Hello, welcome to Forest Learn. In this video, we'll be discussing common mistakes that you simply must avoid when it comes to questions on projectile motion. These mistakes or misunderstandings stem from a lack of understanding of the applicability of the SUVAT equations, and also misunderstandings about the vector nature of projectile motion. In my experience, I've come across a diverse range of students, including those that went on to achieve A or A star, who have made some or all of these mistakes at some point or another. So it's well worth your time to ensure that you don't make the same mistakes. So let's take a look at these mistakes. There are three mistakes that I see over and over again. The first one is that when a projectile is launched, that students think that the initial velocity on launch is 0. And similarly, that if the projectile reaches the ground or the surface, that the final velocity is 0. Now, this might seem quite strange that I'm calling this a mistake, but the thing is, what I mean by initial and final velocities here are not the literal initial and final velocities. I'm talking about the initial and final velocities that you would use in the SUVAT equations. So I'll talk more about this in a moment or two. The second mistake that I see over and over again is that some students think that the acceleration of the projectile changes sign from negative when the projectile moves up to positive when the projectile is moving down. This mistake stems from students forgetting or not realizing that acceleration is a vector, and in the absence of air resistance, the acceleration is constant throughout. The third misconception that I see repeatedly is that students often think that what we think of as the start and the end of the motion is fixed or can't be chosen by us. And this is not true. Okay, what we regard as the start and end is sort of up to us, and oftentimes it's the key to solving the problem in the most efficient way. So let's take a look at these mistakes in turn. The first mistake stems from students forgetting a key principle of projectile motion, namely that the SUVAT equations are valid only for constant acceleration, or equivalently for a constant resultant force, assuming that the mass is unchanged throughout. This means that you have to be very careful about where or when you can use the SUVAT equations. So let's take a closer look at what we mean by this in the following example. Imagine a football that's kicked from rest and comes to a rest when it reaches the ground again. So just imagine that we've got some very thick and wet mud here, and the ball just comes straight to a stop when it reaches the ground again. We'll be assuming that air resistance is negligible throughout. Now, you heard me correct. I did say that the ball is kicked from rest and that it comes to a rest when it hits the ground. But despite this, we can't use an initial and final velocity of 0 in the SUVAT equations. Hopefully the following diagrams will explain why this is so. In this little diagram here, I've drawn the ball and the boot. And just before the boot makes contact with the ball's at rest, which means it's in equilibrium. So what I've drawn here are the two forces acting on the ball. Its weight acting down, and the normal reaction force, which is equal and opposite to the weight, acting up. Now, a very short time later, when the boot actually makes contact with the ball, the boot will apply a force on the ball. That's denoted by this arrow or vector here. And since there's now a resultant force on the ball will start moving. So I should say here that the ball is no longer in contact with the ground. So I haven't drawn the normal reaction force going up, because it's in the air now. Now, a short time later still, the boot will be applying a maximum force on the ball. Notice how this vector here, this force vector or arrow, is bigger, has a bigger magnitude than the vector over here. And notice how the ball has been slightly deformed, okay, due to the force that the boot is applying. So what we've seen here is that from the start up to this point here, the resultant force acting on the ball is changing. And that implies that we can't use the SUVAT equations during this interval of the ball's motion. That's because if the resultant force is changing, that implies that the acceleration of the ball is also changing or not constant. This is just a simple consequence of Newton's second law, F equals ma. Right? For constant mass, if F changes, that means that the acceleration a must also change. And recall that the SUVAT equations are only valid for a constant acceleration. Now, a short time later, the boot and the ball will once again no longer be in contact with one another. So at this point, the only force acting on the ball will be its weight, straight down. And here I've just drawn the ball moved slightly further on. Okay, again, it's in the air. The only force acting on it is its weight. Recall we're neglecting air resistance. And this is great because precisely at this moment here, where the boot and ball are no longer in contact with each other, this is the moment where we can start using the SUVAT equations, right? That's because from this moment onwards, right, until it hits the ground, which we'll discuss in a moment, the resultant force, which is just the weight of the ball, well, that's unchanging, that's constant, and that means that the acceleration of the ball is also constant. The acceleration of the ball is just the acceleration due to gravity, right? So it's at this point here where we can take the initial velocity of the ball, whatever that is, right? So I've just denoted the velocity here by this black vector. Whatever that velocity is, we can use that initial velocity in the SUVAT equations. And just to be absolutely clear, using an initial velocity of 0 in the SUVAT equations would be incorrect for the reasons we just discussed. Now, I mentioned that we'd discuss what happens when the ball reaches the ground. And actually, it's quite a similar story to what we've been discussing up till now. So here in these two pictures here, I've drawn the ball just before it's about to make contact with the ground. Alright, so you can just make out this little gap between the ground and the ball. And if there's no contact between the ball and the ground, then the only force acting on the ball just prior to it making contact is, once again, just the weight of the ball acting down. And this means that we can use the SUVAT equations right up until this point here, just before the ball makes contact with the ground, because the resultant force, which is just the weight, that's constant, and that means that the acceleration is constant. So in other words, what I'm saying is that the final velocity that you would use in the SUVAT equations would be this final velocity that the ball has just before it makes contact with the ground. Now you might wonder why it is that we can't use 0 as our final velocity, given that I mentioned that the ball, once it hits the ground, it will eventually come to a rest. To understand why we can't do this, we need to look at the forces acting on the ball once it makes contact with the ground. So once it makes contact, you can see the presence of a new force or combination of forces acting on the ball. And as the ball comes to a rest, you can hopefully see here that the resultant force on the ball would be changing. And what this means, of course, is that we cannot use the SUVAT equations, because if the resultant force is changing, that means that the acceleration that the ball is experiencing is not constant. And that's why we can't use a final velocity of 0 in the SUVAT equations, despite the fact that, literally speaking, the ball does come to a rest eventually. Let's move on to the second really common mistake, which is that students often think that the acceleration of the projectile changes sign from negative while the projectile moves up to positive when the projectile moves down. And this misunderstanding stems fundamentally from the fact that students forget or don't realize that acceleration is a vector quantity, which means it has a direction. So this is best appreciated if we look at the following example. Let's consider, for the time being, a ball that's just thrown straight up into the air. So it's thrown up with an initial velocity of 10 meters per second, and you can see it moving up, and finally it comes to a momentary rest when it reaches its maximum height. Notice here I've labeled the upwards direction to be positive. Okay, so remember, whenever you're doing projectile motion questions, we're dealing with vector quantities, namely displacement, velocity, and acceleration. So because we've chosen the upwards direction to be positive, that's why these velocities here are positive 10, positive 7. On the way down, however, the velocities are negative, negative 7 and negative 10 at these positions here. And that's because, well, when the ball moves down, what we're saying is that because we've chosen upwards to be positive, downwards motion corresponds to negative velocities. Now, throughout, there's only one force acting on the ball, which is its weight. Again, we're neglecting air resistance, right? So its weight, if this is a ball of mass m, then its weight is simply mg. And of course, to work out the acceleration, we just use Newton's second law, which can be rearranged as a, the acceleration, equals F over m. F, the resultant force here, is just mg. And cancelling the masses, we end up with just g here for the acceleration. Now, strictly speaking, this is just the magnitude of the acceleration. Remember, acceleration is a vector quantity. And since acceleration and force are proportional to each other, whatever the direction of the resultant force, which is just the weight here, that's also going to be the direction of the acceleration. So the acceleration of the ball here is constant and pointing downwards. And since it's pointing downwards, we should say that the acceleration is equal to minus g, because the downwards direction is the negative direction. So in other words, the acceleration, it doesn't change sign. It's constant and always equal to minus g. Another way to see this is to examine the velocity time graph of the ball throughout its motion. So you can see here that the initial velocity of the ball is 10, and when it finally reaches the same starting height, having come back down, its final velocity is minus 10. And you can see that it's just a straight line. And recall that the gradient of a velocity time graph corresponds to acceleration. And it's a straight line with a negative slope. The gradient is just equal to minus g, which is exactly what we said just a moment or two ago. The equation, or the relation between v and t here, is simply given by v is equal to 10 minus gt, because u, the initial velocity, is 10 and a is minus g. So once again, we find that the acceleration does not change sign. It's a constant and equal to minus g. Now, the reason why so many students fall into the trap of this mistake is because that they forget that acceleration is fundamentally defined as the change in velocity divided by the time taken. It's not the change in speed divided by the time taken. So students make this mistake because they look at this kind of scenario and they go, okay, well, as the ball moves up, obviously it's slowing down, right? And they say, okay, well, if it's slowing down, surely the acceleration is negative. And on the way back down, they look at it and go, okay, well, you know, the ball's speeding up again, which is of course absolutely true. So they think surely the acceleration must be positive. But acceleration is not about changes in speed. Okay, it's about the change in velocity. And if we just go back to this graph here, this graph just shows it nice and clearly. The velocity is constantly decreasing, right? It starts out positive, becomes 0, and then on the way back down, it becomes negative. Okay, so try to bear this in mind. This is a really common mistake that I've seen over and over again. Everything we've said holds true for a projectile that's launched not just upwards but also moves sideways, as shown here. So for this projectile, I've shown at these various stages the velocity of the projectile by this black arrow or vector. I've also denoted the components, the vertical and the horizontal components. I haven't marked the values for the horizontal components of the velocity because that's just a constant throughout. Now remember that in projectile motion, the vertical and horizontal motions are independent of one another. And since the initial vertical component of the velocity is 10, just like the initial vertical velocity in this example over here, that means, vertically speaking, the motion of this projectile is identical to the motion of this ball just thrown up and down. You can see how the vertical component of the velocity is changing. So 10, 7, 0. And compare that to over here, 10, 7, 0. Minus 7, minus 10. Okay, so what this means is that the vertical acceleration, if I call it AY, so Y denotes that we're talking about the vertical acceleration, is equal to minus g, just like it was over here for the ball that went straight up and down. And just to be absolutely clear, the horizontal component of the acceleration is 0 here, because as I said earlier, the horizontal component of the velocity is unchanging because there are no forces acting horizontally. Remember, we're neglecting air resistance again. So the vertical acceleration, or the vertical component of the acceleration, is minus g, so it's constant and there's no change of sign. Now let's move on to the third really common mistake, which is that students think that the start and end of the motion, or what we think of as the start and end of the motion, is fixed and can't be chosen by us. So if we look back at the example we've just been looking at, it's natural to assume that the start is when the ball has just left the ground, and the end is when the ball is just on the verge of hitting the ground. And this is a perfectly valid choice to make. However, it's not the only choice we could make regarding the start and the end. Depending on the question and the info given in the question, it might be more convenient or more sensible to regard the end as being when the ball is at its maximum height. And this is perfectly okay, because between the start and the end here, the force, the resultant force on the ball, well, that's just the weight, and that's constant, meaning that the acceleration that the ball experiences is constant throughout, just the acceleration due to gravity downwards. So we can use the SUVAT equations without any problems, and we can perfectly well take the start to be here and the end to be when the ball is at its maximum height. Now, here's a chance for you to have a go at a question yourself. A golf ball struck from the surface of the moon had a time of flight of 5.0 seconds. What was the maximum height reached by the ball? The acceleration due to gravity on the moon is 1.6 meters per second squared. So please pause the video to have a go at this by yourself, and when you're done, unpause the video and we'll go through the solution. Okay, welcome back. So it's always a good idea with these kinds of questions to just draw a little sketch of what's going on. Also, I've chosen the upwards direction to be positive, just as before. Recall that we also have to choose a start and end for this motion. And again, you might think it's natural to choose the start to be when the golf ball is first hit and first leaves the golf club, and the end to be just before it hits the ground. But actually it will turn out to be better to treat the start to be when the ball is at its maximum height, and the end to be just before it makes contact with the ground. You'll see why this is a good choice shortly. Now what we're interested in, of course, is the maximum height. And so if we can figure out the displacement between the vertical displacement from start to end, then we'll get the maximum height. So let's start drawing up a little table of what we know. So in the vertical direction, we're trying to solve for s, so that's unknown. If we're taking the start to be when the ball's at its maximum height, recall that at its maximum height the ball will be moving horizontally. And that means that the vertical component of its velocity will be 0. Right? So u, we can say equal to 0. V, the final vertical component of the velocity, well, that's unknown. Because remember, the final velocity is the velocity of the golf ball just before it hits the surface. Remember, once it hits the surface, the ball is no longer experiencing constant acceleration, and therefore the SUVAT equations are no longer even in play. The acceleration between start and end, well, the ball's just experiencing a constant downwards acceleration, the acceleration due to gravity on the moon. And because we've taken the upwards direction to be positive and the acceleration is acting downwards, the acceleration should be minus 1.6 meters per second squared. Now if the time of flight from the start, from the launch point to the end here is 5 seconds, then due to the parabolic symmetry of the trajectory of the golf ball, we know it will take half as long for the golf ball to go from the start, so from the top here, to the end point. So the time for us, the time taken between start and finish, is just 2.5 seconds. So from this we have enough info to actually solve the problem. We don't even need to consider what's going on in the horizontal direction. In fact, we're not even given any info regarding that. So what we can do is we can employ the SUVAT equation S equals ut plus half at squared, and pop in what we know. So we're trying to solve for S. U is 0, so that means this first term here, u times t, just disappears, and we're left over half times a, which is minus 1.6, times t squared, so multiply by 2.5 squared. And if you work that out, you get negative 5.0 meters. And the negative here makes sense, because in going from the start to the end here, the ball has moved downwards. So it's undergone a negative displacement because the upwards direction is positive. So therefore we can say that the maximum height that the ball reaches is simply 5 meters. Or 5.0 meters. To two significant figures, which is what we should be working to, because all the info given to us in the question is to two significant figures. You could also have solved this problem by taking the start to be down here and the end to be at the maximum height, and employing the SUVAT equation S equals Vt minus half At squared. I'll leave that to you as an exercise to see if you can arrive at the same answer. Had we taken the start and end to be kind of what naturally one would assume the start and end points would be, this wouldn't have been very useful, because in going from the start to the end here, the vertical displacement is 0, right? And So that's not terribly useful. I mean, we can pop that into this equation here, for example, and still get some information, but it's a much more long-winded and indirect route to the answer compared to the solution we just sketched out here. While in this video we've been talking about common mistakes to do with projectile motion, so the motion of objects moving under the influence of gravity, it's really worth noting that actually projectile-like motion can happen in other scenarios or in other phenomena. So for example, this positive ion here, if it enters this region in between a electrically positively charged plate and negatively charged plate here, it will be deflected downwards, much like a parabolic path of a football or a golf ball. Okay, and actually the positive ion here would experience, to a very good approximation, a constant acceleration. So that means the SUVAT equations would be in play here. So it's really worth ironing out any misconceptions you might have regarding SUVAT and projectile motion type questions, because it will hold you in good stead when it comes to tackling other parts of the syllabus. If you found this video useful, please like it, share it, subscribe to the Forest Learn channel if you haven't already, and if you have any suggestions or questions, please leave a comment. So thank you for listening, and I hope to see you soon.